take absolute everyone silence as we go into this. Thank you for your understanding. Dr. Azike, we will be waiting for you to share the screen and go on with the presentation.
Hello? Are you hearing me?
Yes, we can hear you.
Can you see my slides?
Yes.
What do you see? For example, are you seeing the full slide? Are you seeing it with the speaker notes?
Yes.
Yes, it's in full screen mode.
No speaker notes, right? Because I want to make sure that it's large enough. Thanks for confirmation. First of all, I want to thank NAPE Nigeria for this opportunity and the last speaker for the introduction. My name is Ogochukwu. You can call me Ogo. Zeke is my surname. And this is a part of chapter 1 of my dissertation of PhD research at University of Texas, Arlington. And my supervisor and advisor was Max Hu, Professor Emeritus. Presently is in Shandong Provincial Key Laboratory of Deep Oil and Gas, and also interfacing with the University of Texas at Arlington.
Okay, are we going all the way back?
I think someone is interfering with the presentation. Please, can you mute your gadgets, maybe phone or computer? And secondly, can you confirm if I am audible enough before I proceed?
You are audible enough. It's okay.
Okay, and the topic of my discussion today is laboratory analysis of mineralogy, pore connectivity in Silisiclastic, which are mostly sandstones, and the carbonate reservoirs of Denver Basin. I also want to add that this is a part of what I also did in another basin, which is the Williston Basin in the United States of America. Before I go on, I want to show the outline of my presentation, which involves introduction and the study objectives that led me to this particular research, the general information on the study area in terms of the expected stratigraphy and the general information of the depositional environment and the rock characteristics, and also the hydrocarbon producibility, because this is not just an academic exercise. This is an exercise that will be tied to productivity in the oil and gas. And I also want to mention that the driving force is also related to the present drive for energy transition, especially when it comes to geothermal energy, of which the understanding of oil and gas will be applicable in such new development, which can also be related to what happened in the last 10 years in terms of development of unconventionals, of which the conventional understanding was, used. So, based on my, on my last statement, having worked in the industry with experience in Niger Delta Basin and Anambra Basin, Nigeria, and other basins in the United States and Asia, including some parts of Middle East as well, of which the reservoirs consist of unconventional and unconventional reservoirs. I've observed disparities in the geomechanics and the petrophysical properties characterization due to different scales of measurements and methodologies. My industry experience in 3D reservoir static modeling for field development and production optimization projects including borehole geology and horizontal well geosteering, enable my understanding of data integration in terms of understanding the pore structure, of which the resultant of your interpretation is highly dependent on the scale of your data. What I mean by that is if you have core information or if you have well log information or even recording some more log, these are different scales of measurement in terms of their size when you want to relate it to their ability to maybe image or define the formation, or even when you talk about resolution. Even with logs, they have different resolutions. So that is what I mean by multi-scale. And although this presentation is kind of more of mineralogy and pore connectivity characterization, the combo of the study includes diffusivity measurement, of which is applicable when it comes to CO2 sequestration in the United States, because the chosen areas for these studies were basically the areas that were mapped for enhanced oil recovery and carbon capture and sequestration in the future. And because of that, I looked at the data that has been processed in past time, and I came to conclusion based on literature review that most of the studies were kind of limited within the reservoir of interest. Of course, that is expected because if I'm drilling for oil, I just have to consider where I have my pay. I don't need to go to non-pay. So that is what led to my looking at different stratigraphic sections from top to bottom in a stratigraphic sequence to understand the areas of which we are not studied in the past. So, and that comes to the question of how are you going to do that? Can you have core data in all the sections, which is impossible because of the cost and doability. But sometimes you can have recordings and well log in all these sections. So in that case, what can you do? And that is what led to the problem statement and the study objectives. Are you seeing the screen? Is everybody seeing my screen? Because I'm seeing a pop-up question of, can you see the screen right now? Is anybody having issues with visualization of my screen?
Yes,
Oh,
yes.
okay. Okay, thanks for the confirmation. So the area of study, oh, sorry, that's supposed to be our area of study, general information. So the area of study, we have two major reservoirs here. If you look at it, this is the lower Cretaceous reservoirs and the upper Cretaceous reservoirs. In the lower Cretaceous, we have mostly the more DJ sandstone, which are generally the Dakota sandstone. We have most of us must have heard of Niobrara Formation. So Niobrara Formation could be more argillaceous or more or more carbonaceous, depending on the area, because this basin cuts across different states, and this is what I mean here. So this is the area of study. This is another area of study, but I'm not presenting this today. But why I show this is to kind of highlight that what I did here was also used to see how it relates to what was done in the other basin. So this basin is large in the sense that it cuts across Nebraska, Colorado, Kansas, and the other neighboring states. And if you look at this, I have well data, and this well data is what we use for these studies. And the significant reservoirs that we chose in these studies are the Niobrara Formation and Dakota Sands. And the current production in this basin is about 520 to 620,000 barrels per day, with a historical cumulative production of more than 1.1 billion barrels and 4 TCF of natural gas. In terms of deposition environment, the Niobrara Formation was deposited in a shallow water environment during the late Cretaceous period and was characterized by low clastic input, which led to the formation of carbonate sediments like chalk, marl, and limestone composed mostly of coccolith shells. We're going to see from the mineralogical analysis when it comes to the lithologic description. The other one is the Dakota sandstone, which is Upper Cretaceous, and primary sandstone and shell of the Taik and nearshore marine environment. And the purpose of this presentation, one of the purposes is to see how that compares with Niger Delta reservoirs. For example, in the northern Delta depot belt, most of the reservoirs that I have worked on, and most of the OML is characterized as mainly shallow water depositional systems in a coastal to the Taik environment and nearshore environments, which lithophases could include stacks/amalgamated tidal or fluvial channels and shore face deposits with some shell and heterolithics. So, there is a kind of relationship when it comes to lithology, a comparison of these two basins and the position environment. So how can that relate to the petrophysical parameters and the petrophysics outputs as we move on? The available data include data from 3 wells, and these wells are located in Denver Basin, and these data were provided by United States Geological Survey, Mineral Resources, which are the oil and gas companies, and some of the study equipment we have from University of Texas, Arlington. I want to mention that every data collection involved in this study was free of charge, and the government, which is the USGS, is always helpful when it comes to availability of data. And most of these companies, whenever they drill their wells, after some time, the wells are deposited in the state directory, and it is open for everyone, including students, to take and use it to do whatever they want to do, because the agreement you have as a student in the university, especially in UT system, is that you're going to get data free, and the results will be sent to the USGS, and that allows for collaboration for students, industry, and the government. And this is the message I want to preach to my people, Nigeria, because I'm part of the system. I'm still in the system, and though I'm in the US, I will still come back to the system. So in terms of data availability, here we have the core. So I went to the USGS and I got this core information, and this was also provided by the company. So what you see here are the log samples, and these are the core, like I said, and 3 cuttings. So these cuttings, one of the things that was involved is, it comes in bags, right? So the first thing I did was to define the stratigraphic sections using the well logs that was provided and more log information, which is this. With that, I was able to define unique zones which have similar petrophysical parameters and tie that with the formation of interest. And after I have done that, I had to clean it and do oven drying at 60 degrees centigrade for about 24 to 48 hours. And then I did my GSD, which is grain size distribution analysis, into different fractions. As you can see here, the higher size is a GRI plus. So these are the nomenclature I used, but these are the sizes from 1.7 to 2.36 mm to the least, which is the powder, and that is what you see here. So the question is this: somebody may ask, why do I have to do this? Because if you look at this, you find out that experimental and laboratory analysis and even previous studies from people have shown that the variability and the results that you can get is dependent on the grain size and the distribution. So that was done, and these are the inputs for this study. And why did I consider this general input? Is because they are readily available in the industry, and most times these are thrown as waste, and everybody's looking for well logs. and core information. But the question is, based on my previous studies, there are some problems we have solved in field development just with mud log information and ray cuttings. So the laboratory experiments that we have, in this include two areas. So since I have ray cuttings and cores, there are some that could be done with ray cuttings and some with cores. So that's what you're seeing here. I'm not presenting this. This is something I may present in the future for the organization if invited. And today I will talk about XRD and X-ray scattering. I will also talk about spontaneous inhibition and liquid immersion porosimetry. So the laboratory experiments, like I mentioned, include like XRD, ultra small angle X-ray scattering, density, TOC, gas diffusion, and MICP can be performed with granular cuttings, unlike these experiments. That's why it is mapped out this way in terms of methodologies. And why I mentioned TOC density is because for you to even do USACs, you must have done your XRD and TOC because they're part of the input for the interpretation. So I also did TOC analysis, but I'm not presenting it today because of time constraint. So for example, for the XRD, this is available in the university. So we have this, and we have, this is one of the latest one we have. And the quantitative mineralogical analysis are usually performed on ray cuttings or even when you are crush core using X-ray, XRD in combination with other measurements such as analysis of the bulk elements, particle and bulk densities, which I had to compute for each of these samples. And the most important thing is that so you have to grind the cores and the ray cuttings to powder sample size. And what you have here is, I don't want to go deep into this, but these are input parameters. For example, in the lab, I had to use input parameters like setting on the voltage and current in a stepwise process to 40 kV and 30 mA respectively. And I also have to set the tubes. You have tubes here, the tubes and detector distance and the two theta angles, which were set to continuous cam mode with a range of 2 to 70 degrees. And this what you have here is the raw output that comes from XRD analysis, which we now take to this software called MDIJ9 software for you to now interpret your mineralogical constituents in terms of percentage per sample, as you can see in this. So with this, you have a kind of finished your XRD analysis, and all this were done in the school free of charge for the student. So results and discussions as it relates to what we are talking about. So the question is, how does this imply in the industry if I have cores and cuttings of the same formation? If you look at this, you find out that if you look at the ternary plot adapted from Schlumberger classification scheme of 2014, you can see that both samples from cores and cuttings, including lithology from mud log, for example, for Niobrara Formation, are all depicting carbonate. The question is, what percentage of siliceous materials is present? And you can see they are different. The ones from cuttings is more siliceous, and the ones from core is less siliceous. And the question is, why is this happening? And that is one of the things that we try to solve in these studies. This is also shown here because if you look at this, you find out that out of 91 different experiments with variable grain sizes, what I mean by variable grain sizes is that, like I showed when like I showed previously in the grain sizes, this is size A, this is a large size, this is also a large size, these are small size A and B. those ones seem to have more siliceous content and less carbonate content. But when the size is increased, like this size A, you find out that it matches more to that of core. So this is very, very important, and it allows you to kind of make your choice in terms of what size am I going to use if you want to do my analysis with cuttings. And from this research, we found out that the bigger the size, the closer you are to what you can get from a core information. And what you have here is, okay, I tried to plot a radar chart which shows XRD from cores from Dakota, sandstone, and Niobrara formation. The dominant minerals, as you can see, are quartz, you see here, and elite clay type minerals. And the Niobrara formation also has pyrite rich, which plays a significant role in the formation of organic matter in sediments, particularly in the presence of organic carbon and iron availability. The oil and gas production from this formation are tightly linked to the kerogen content and thermal maturity. It is important to note that in this particular reservoir, the presence of elite type clay, which exhibits limited swelling compared to smectite, when in contact with water, are important for hydraulic fracturing, which is important in the area for horizontal drilling and production optimization. And if we compare this with Niger Delta Reservoir in terms of quartz content, this is a study from Ovarere et al. 2024. You can find out that both has clay content variation, that they don't have the same, but both can be categorized as quartzose sandstone. But the feldspar contents are different, and also the clay content is also different. That is what we observed from the experiment that we have. And I also try to look at other information from the studies. And I found out that there are also trace elements occurring as ferron calcite cement, represented as FC and siderites. And although these are, they are trace and probably discontinuous and unlikely to represent significant barriers to fluid flow, the understanding of all these diagenetic minerals, especially when it comes to cementation, is significant, because if you have a reservoir that is depending on the variability and the cementation in the reservoir and the extent, it could impact on your flow. But if it is not much distributed, I don't think it will be much important. But it's good for us to know that some of the reservoirs in the Niger Delta can also have carbonate cement. But in terms of similarity, they are kind of similar in terms of the mineralogy, but not exactly the same. So that is that for this. So the next experiment that was done is ultra small angle X-ray. So this method can measure total porosity, including both age-accessible and isolated pores in granular or crushed cores. Okay, the schematic diagram you are seeing here, is just a principle of a small and wide angle scattering with intensity distribution measured as a function of a scattering vector, which you can see here. And these are the samples, about 58 samples that I loaded in this sample plate and was taken to Adjunct National Laboratory, which was established in 1946 and is the U.S. first national laboratory. And what you see here is the scattering intensity, total scattering length density, which I was able to compute from information from XRD, TOC, and also the atomic number and and the molecular constituents of the minerals of interest. And why this is important is that if you are working on unconventional reservoirs, you have to also consider the porosity attributed from the micropore to nanopore scale, because this cannot be determined by most measurements, especially from conventional measurements. So this is more or less unconventional related. So when the introduction for this presentation was done, there was a statement of challenging reservoir understanding in the future. So it means that as the time goes by, we may stand up, we may start looking into some reservoirs that may be considered as low producers. And if you look at this, you find out that on the left side, you have the pore through distribution, and the pore sizes from 1.2 nanometer to 100 nanometer to 1000 nanometer. This is an example from Niobrara cuttings. So from cuttings, you can even do sacks, experiment. And after doing this, what I did was to look at various literatures to see how it compares. And these studies by Juan and some of his team in 2017 also showed a bimodal pattern of pore distribution in this formation using core sample. But in my own case, I used Dre cuttings. And you can see that this also shows bimodal pore size distribution with peaks at 2 nanometer. And if you look at this, the peaks I have is in the range of 2 to 50 nanometer, which is this, and 460 to 600 nanometer, which is within the range of 100 nanometer to 1000 nanometer. So you can see that even from cuttings, you can also understand the incremental surface area. So the smaller the pores, the higher the incremental surface area. And this can create strong capillary forces in the oil and gas development, because the higher the SA, the more the formation will hold water tightly. And in terms of wettability for hydrophobic rocks, the increased surface area will also increase wettability. I also want to point out in this slide that we have two forms of porosity. We have the incremental porosity, and we also have the cumulative porosity represented in different cuttings, in different colors. You can see that for Dakota sand, it has more cumulative porosity compared to the Niobrara. And this is very important because if you are able to compute your cumulative porosity in low pay, in reservoirs that we can consider as low pay, because in the Niger Delta, we also have low pay reservoir characterization, which in most cases, if you run your log, the gamma ray may appear very dirty. And if you look at the gamma ray, the density and the resistivity, you may end up discounting it as non-pay. But surprisingly, some of these reservoirs, especially the ones that is connected to a larger pool in the Niger Delta, has outproduced the initial estimated reserve. And what is going on there? And that's a big question. It could be related to, non-characterization of micro pore porosities, because an increment of porosity in the range of 0.1 to 2% can make a big difference in terms of porosity cutoff. Because if you do a cutoff of a pay of maybe 10%, and then you are able to, and you don't include the micropore porosity, which might be 2%, you may end up cutting off 8% porosity interval, which cumulatively is 10%. So, and that is very, very crucial when it comes to low pay reservoirs. So the next one I want to talk about is liquid immersion porosimetry for the determination of edge accessible porosity, pore structure investigation, and is a measure of effective porosity. So the most important thing in this experiment is that if you look at this, you will see that the core plugs are just the way they are from the lab. So it's non-destructive experiment. So when you want to perform an experiment as a researcher, you have to design your project in a sequence that relates to what you want to do. Because if you start crushing your rock before you start doing your LIP, you may end up having a problem. So understanding of the processes is crucial even before you start the experiment. So I want to mention that this was done at the lab, free. What we did was the porous media lab was able to, so this was fabricated locally. This can be made in Nigeria by any welder. It's a very simple thing. The job of the department or the industry or whoever that is involved is to make sure that this can form a seal when you lock it. So this is put inside this place, and then I use these screws to tighten it. And we have this grease that we use in grease the top so that there won't be any air coming in or going out, so it's airtight. And we connect this to maybe water or salt, depending on what you want to use as your fluid phase. And this is connected to vacuum pump. This is a vacuum pump down here. We can always buy vacuum pump. And then the next one is connected to a cylinder. And that's it. And this experiment is not that expensive because a complete run of vacuum saturation can be done for up to 30 to 40 core of this size. And each run, which could last for like 2 days, will cost less than $20. Why I'm saying this is because I'm not just making a presentation in terms of academic research, but applicability in the industry. And these are the equations that were used to determine porosity and grain density, bulk density, and gravimetric water saturation. What you have here is a result of the previous experiment description I did. For different samples, we have all this information. We computed the bulk and grain density and the porosity. With that, we computed the gravimetric water saturation, which was multiplied by the density, the bulk density, to get the volumetric water saturation. And this was also compared with Niger Delta, studies for carbon capture and storage in depleted reservoirs. And these are the values we have for the water saturation, the porosities. We are also in that, presentation. So in essence, the microstructure and pore geometry can impact, the fluids interaction with the rock. For example, a rock with complex pore geometry can have a lower saturation. So sometimes when you're looking at the water saturation and the porosity relationship, it doesn't necessarily mean that if you have a higher water saturation, it means low porosity or high porosity. It depends on so many factors. For example, a rock with high porosity can still have lower water saturation. The pores are filled with other fluids like oil and gas. But in terms of comparison with these studies, I found out that the samples I had were cleaned and oven dried, implying that what we have is just the pores, which is close to 100% because after cleaning and several hours of drying, I don't think there is still any other fluid in there. So when compared with the Niger Delta, this area is more tight. Niger Delta has a better reservoir, properties, and that is why some of the reservoirs are considered as unconventionals in the basin. The last experiment that I did in order to understand the pore connectivity is spontaneous imbibition. So imbibition is said to occur when a porous medium containing non-wetting phase is brought in contact with a wetting phase, and the wetting phase spontaneously displaces some of the non-wetting phase. So the simplest example is you get a tissue paper and you place just the tip of the tissue paper in a glass of water. You will see that the water will wet the tissue and travel upwards against gravity. So in essence, imbibition is a capillary force control process. and it plays a crucial role in petroleum production for both conventional and unconventional reservoirs. So what we did was that this can be replicated in Nigeria because we can always get analytical balance. I had my undergraduate at University of Port Harcourt, Nigeria. So we can always get this. This can always be bought. And then what we now did was to hang this to something we can use to hold the core that we have already prepared by cutting it into 1.5 centimeter height and 1 centimeter diameter. You can choose any size depending on what you want to monitor to limit the water absorption and age-based imbibition, because we want the water to just flow vertically. So we had to coat the sides with quick cure epoxy, except the top and bottom. So what we now did was to suspend this sample from a high resolution balance. What I mean by high resolution balance is that this can measure up to 10 units, like 0.00000 up to 10 units. And the sample is suspended from a high resolution balance with bottom of the sample tip just contacting the liquid solution, and the suspension of the sample into the fluid. As long as once it touches the fluid, you start the imbibition and you start logging. And a typical process is to log the first 2 minutes. It's going to rise fast the first 2 minutes because of adhesions and the meniscus around the sample. And then every 30 seconds for the next 2 hours, and then you can proceed to 2-minute intervals. That is what we use for the processing. And to describe imbibition, this is the equation, of which QW is the total volume of water imbibed in centimeter cube. PC is the capillary pressure, and this KW is the effective permeability of the porous medium to a wetting fluid. And this is the cross-sectional area, and this is the viscosity. So with this equation, it can be deduced that from the imbibition, you can get your qualitative understanding of pore connectivity and permeability because of the processes that I have described. And these are some of the results that we have from previous studies by who? It's al, which is my supervisor. We have, we're able to characterize different kind of rocks, including cement. And we found out that the slope of high pore connectivity should be greater than 0.5, while the highest slope of the minimum of less than 0.26 is low pore connectivity. The most important thing is that if you look at this, I have S1, S2, and S3, which are 3 different slopes, because we can't just join this as a common line. You see what's going on here at initial time. You see that there is fast rising of the fluid in the formation due to adhesion within less than 60 seconds, which is what you see here. And then there is another one which is slower rising, as you can see. And the third one is this one that are called here, which is stable stage. And this is what determines the pore connectivity, because at this point, it is the matrix porosity that really plays a role. In the second stage, it could be due to microfractions and laminations. And because these reservoirs can be considered as unconventional, they have both a fraction and matrix porosity, which can be combined for more effective porosity. Another thing to point out here is that this and this are the same sample, but different time to reach the top and a different rate of fluid saturation. The significant difference is the fluid type. This is brine, which is salt that we prepared in the lab, and this is the air distilled water, which we call a DI fluid. You can see that the porosities are the same. And significantly, when we have a lower porosity, for example, it takes more time, and then when you have a higher porosity, it takes less time. For example, this particular sample has a porosity of 25.41, while this one has a porosity of 15.22%. You can see that it took almost 1 hour before it gets to the top. of this formation, but it took less than 30 minutes for it to get to this formation top. So this is an indication of poor connectivity. So the question is, if we have several stratigraphic sections and we, do this experiment using the previous information I showed in the methodology, we can understand the poor connectivity on a reservoir scale, and hydrocarbon recovery from fracture reservoirs is strongly dependent on the spontaneous imbibition, whereby water is imbibed into the rock matrix blocks from the fracture, resulting in oil and gas displacement by water. So the next one I want to show is, comparison with the Niger Delta. The figure you see on the right, the figures you see on the right show the experimental result of oil recovery and the square root of imbibition time at different interfacial tensions. This is what I mean. These are IFT of 23 dyne per centimeter and 26 dyne per centimeter. And these are the petrophysical parameters for all the samples. For example, core 1 is 2116, and core 2 is 2009, and this is 2060. So if you look at this with the porosity and you can compare that here, you will find out that there's a difference for the same permeability, but look at the recovery rate. So what played role in this? How do we compare it with this area? You can also find out that, for the same formation using different fluid types, for example, brine and DI water, you find out that there is also change. For the areas that we used DI water, you have a higher fluid saturation, and the fluid was able to imbibe faster. And if you compare that with this, it is also applicable because if the samples with higher interfacial tension from Niger Delta behave like these plots from this Niger Delta rocks, because in this case the dissolving salts increases the surface tension and strengthen the bulk cohesive forces, resulting in reduced imbibition rate, like you see here. When this sample with a greater interfacial tension is, the results in terms of recovery of oil is less compared to when we have reduced interfacial tension. So the laboratory techniques that we have can also be applied in other approaches for comparison. So even if I don't have the resources for me to perform this more expensive experiment, I can do the one that is less expensive to have qualitative information, which can lead to understanding my reservoir for optimized characterization. This is the conclusion of this research presentation. So we're able to define the pore types, distribution and connectivity using a different range of experiments for different scales of data, which include the contents, the mod log, and the core information. And I also want to mention that I observed some disparity between drill cuttings and core data, and it's because of the reduced granular size, which increases surface area of the crushed rock formation. This is very crucial when it comes to use of drill cuttings. And this novel experimental approach with multi-scale data deliver qualitative information. And the comparison of Dakota sandstone formation showed that some of the petrophysical parameters were similar with Niger Delta study examples, which is also sandstone. The results from this research are essential for selection for EOR and CO2. And I also want to mention that in the United States presently, because this is oil and gas, so we need to think beyond oil. It is good that the NAPE, before it used to be our ideas find oil, but presently it has gone beyond oil, which is cool because here in the States, where I am presently, situated, I can say that, for example, right now I am working as a postdoc research fellow at United States Department of Energy, and at their office in National Energy Technology Laboratory in Pittsburgh, Pennsylvania. Well, the major focus as of today is not just oil and gas, but carbon sequestration and storage. And if you have been listening to news of recent, critical minerals is the major play today. So the question is how we're going to apply this, because most of this information are not available, especially in most of the reservoirs, because of the concentration only in oil and gas. So I want to acknowledge the laboratory, the school, which is the University of Texas, Department of Earth and Environmental Sciences, for their financial assistance and laboratory apparatus. I want to mention, because I'm a Nigerian, that the only money I spent in this research was driving myself to the school for about 3 or 4 times in a week, because some of the experiments we are done overnight. You leave it and run. If light goes off, you have to rerun it. So having power is very important. And I also want to mention, as a Nigerian, that the data were freely donated and readily available online. I can always go online. For example, Texas Railroads Commission, if you can have access to that. If you can't have access to that when you're in Nigeria, if you cross over to the United States, you can always pull data. And I also want to thank NAPI, Nigeria Benin chapter, for the invitation and opportunity to present my research work. I want to thank everyone here, and I also want to say that I am not just doing a postdoc research fellow, I'm also a consultant for a lot of FDP studies in Nigeria. I just completed one not long ago, and although this is US presentation, but I am more of a Nigerian reservoir geologist. Thank you so much, and remain blessed. Hello? Hello?
No, I can hear you from my own head.
Oh, okay.
Thank you so much, Azike. That was very well presented.
Can you hear
We can
me?
hear you very clearly.
Okay, you heard me even at the end, right?
To the very end, yes.
Oh, okay. Thank you so much.
Thank you very much. Ladies and gentlemen, you will agree with me that was quite insightful and educative. It is also good to note that one of our own is making giant strides right there in the United States and being able to relate it with the Nigeria also from where that's started from. In order for us to progress this technical meeting, it is time for the recap by the chairman. He is going to recap the presentation. And it's also at this time I would request that everyone with questions should please go to the Q&A box and drop your questions with your affiliations, name, and where you represent. In the meantime, please let's once again appreciate and welcome the chairman of this technical meeting, Mr. Martin Mali, who give us the introduction.
Thank you, audience, Dr. Ogochukwu for this wonderful presentation. It's really quite inspiring. As a part of the mark to that's the recap position, we remember the aim and objective of this is more to scale laboratory characterization for geological properties in Denver Basin. Actually, the presenter, when I to state the initial the settle of problem for this research. And actually it provides based on the lack of reference data for the efficient options and backup for activity, especially in the shale oil reservoir. And this has been a challenge in the industry, and not only is needed to the reservoirs in United States, it's also common also in the Niger Delta. So this research actually is well applicable here in Africa and especially in this Niger Delta. The researcher had some the data he used, like the core data and drill cotton sample used for his analysis. And the methodology adopted for this research based on what we saw in the presentation, X-ray diffraction for mineral identification and quantification. It also uses for transform angle X-ray scattering for pore size distribution analysis. We also use the liquid immersion porosity for porosity and water saturation verification in the course of this research. And also another tool we use is spontaneous elimination for the pore connectivity assessment. And from this research, what are the key results? Based on the presentation, and the key result and insight from this presentation that's all related to mineralogy. That the grain sizes, the sample depth affect the mineral variability, and the differences are so pronounced as the lithology transition period. And also the researcher when I went to study the porosity types, and he categorized the porosity into three. We have the macro porosity that's greater than 50 millimeter macrons, and the mesoporosity, the mesopore and macropore. And also based on the research, we're able to learn that the larger surface area are found in the macropores area. And the increased surface area is an indication of irreducible water saturation and wettability. And also the course of presentation, the porosity and water saturation suggests an enhanced connectivity where you have the high water saturation and high porosity indicates the poor connectivity. The intermediate that helps to maintain the porosity and also the cost cementation. And also the low connectivity, the assessment also stored via the emission rates. The higher slots indicate a better connectivity. And also the connectivity depends on both macro structure and secondary porosity features. And the presenter one is very simple for us to apply in our setting. Based on comparative analysis of the data data. Based on the comparison, we go to know that the Dakota sandstone formation in the United States shows similar geological properties to that of data data. And in conclusion, we discover that this research has some novelty in it, like the approach to the way we provide the qualitative permeability saturation across the assessment in Silisiclastic rocks. And this research is very significant and crucial in selecting data types, experiment method, and geological units for enhanced well recovery and carbon capture. Indeed, the finding actually supports reservoir characterization and project planning. So based on this one, the discussion has been today, just to an online publicity here and call on you to ask their questions in order to bring out the more points here. Thank you very much, Dr. Ogochukwu. The floor is open for question and answer. Thank you.
Thank you very much. Thank you, Mr. Chairman, for a very wonderful recap. We will be quickly taking questions and answers that have been put in the chat box. And I have seen a couple, but around the room as well, we will have people who want to ask questions. We will have that opportunity. So, from Roman Aki, if Dr. Ogo is listening, this question is for you. It says, if I may ask a quick follow-up related to pore connectivity, considering the global shift towards CO2.
Excuse me, can you type the Can you type the question? Your sound is muffling, and I think other people have also stated that in the webinar chat. If the question can be typed for me to see while you read it, I think that would be preferable.
Okay, can you confirm if it's clearer now, the voice?
Yes, this is perfect.
Okay, so this is excellent voice coming from Benin. It is not aided. So if I may ask a quick follow-up related to poor connectivity, considering the global shift towards CO2 storage and geothermal energy, could our understanding of poor connectivity and mineralogy from hydrocarbon reservoirs be directly applied to predicting reservoir performance in those cleaner energy systems? The question is asking if the understanding of connectivity, the poor connectivity and mineralogy from hydrocarbon reservoirs, if it can be directly applied to predicting the performance of reservoirs in those cleaner energy systems. So, Doctor, that question is for you.
Okay, thanks for the question. So, first of all, in terms of poor connectivity, yes, because when you are talking of CO2 injection, there are two purposes. It could be for storage. It could also be for production enhancement. And if you are in a very porous reservoir, well-connected reservoir, the dynamics of flow is not the same when you are in a tight formation. For example, there are some areas that diffusivity may be very, very important. And in that case, understanding the pore connectivity, which relates to the diffusion coefficient, is very, very important, because when you are looking at gas, you want to understand how the gas travels. So understanding of a pore connectivity is crucial. And in this study, if I go back and show the stratigraphic section, I considered also non-reservoir zones, because if we are talking of carbon sequestration, we have to consider not just the storage, but the ability to hold what is in place. And in terms of mineralogy, yes, you need to know because of reactivity. You need to understand which minerals can react with a particular gas. And if that be the case, is there anything we can do to, formulate some synthetics that we can use to, limit the impact of different minerals interaction? So yeah, in a nutshell, yes, it is applicable and very crucial for optimized production and storage.
Thank you. Thank you, Doctor. As a follow-up to that question, someone also wants to know if it aids enhanced oil recovery, if this understanding of pore connectivity also aids enhanced oil recovery. So I think it's a follow-up to that question, even though it's asked by someone else. So if you would just quickly add that to the answer of that one, please.
Yeah, when it comes to enhanced oil recovery, although there are several methods, you can use steam injection, you can use water injection, you can also inject back the saline fluid, which is the formation water from the formation, right? So, and in some cases, you can also use gas. You can take the gas back to the formation to increase your reservoir pressure. Yes, like I mentioned, pore connectivity is related to permeability, which is related to transmissibility and diffusivity, of which these factors can be tied into productivity and reservoir performance. So I don't know if that answers your question or you want further clarification.
I doubt there's a need for further clarification. That succinctly answers the question. Thank you, Doctor.
Thank you so much for the questions.
Yeah, the next question is from one of the in-house people who is seated here in the hall. He says, how can results from laboratory studies be scaled up to field level reservoir models? This question he asked says, it's cause, how do we take small scale laboratory results and be able to apply them accurately to build or calibrate large scale reservoir models that represent an entire field, considering that this is minimal small rock samples, maybe a few centimeters in size, and we're talking of a real world where reservoir covers several kilometers with more complexity and variability. So the questionnaire wants to know if this laboratory work is scalable, and if yes, then how?
Question, because someone who is coming from the industry and still in the industry like me, this is a problem because if you how many sections can you take core samples? But what we have found out is like according to DPR regulation, when you drill, I think I can't remember where it is 3 or 4 wells, you need to core one well. And the coring of the well, you have to consider the sections that you have more challenges from the well logs. So to answer your question, if you look at what I've done, I was able to, determine, the pore types. I was able to even estimate porosity, and I was able to estimate even grain density and also bulk density, which we can use to tie with the pore to determine our water saturation. So yes, I also want to say that in this research, I had log information which I used to calibrate with the information from core, even though that it is like a pinhole camera information in terms of size relative to the reservoir thickness. Yes, it is applicable. And I also want to mention that, what I even presented today shows that if you tie the core, which is within a section, with the cuttings, which is in the whole sections, there is a direct relationship. So in terms of reservoir modeling, it is crucial, in data integration. But one of the major challenge is the reservoir modeler, in the sense that understanding your measurement reproducibility and uncertainty relative to geostatistical analysis is very important, because that is what we can use to apply the whole wide reservoir modeling for understanding of your field, static state, and dynamic state. Thank you.
Thank you very much, Doctor. Thank you. I think that clearly answers as well. I have a couple of more questions, if you don't mind. The first one is, what are the main challenges or limitations that you faced when you were carrying out your research? How can we anticipate or mitigate these in our applications, considering that we're looking at the scalability? There are limitations or challenges during the laboratory work. Maybe we can anticipate them, and also how do we go around mitigating them when we want to scale up? So I think that's the question.
Yeah, one of the findings in this research, for example, for XRD mineralogy experiment, a choice of your sample type and size is very, very crucial to tying mineralogy from core data. And I was able to deduce that instead of grinding or crushing your sample and then sieve it to get the powder sections for XRD is not a reliable method, because you are going to bias the mineralogies in the sense that you may end up, choosing the lower end minerals that are softer than the harder minerals, because those are the ones that can easily break down. So yes, there are some limitations. And what I did was, for example, to crush a particular rock sample 100% to a powder, and there is no sieving because I want to get it all. And I also noticed that for likely errors from XRD is that some grains or crystals with preferential orientation can make certain peaks disappear, in the XRD. And when it comes to experiments like SACS, you can have a contrast with wrong rock matrix scattering density, which is SLD, and density values. And sometimes the sample thickness and heterogeneity can introduce multiple scattering effects, and that will affect your pore characterization. So the mitigation I used was to properly check for input parameters for each mineral contrast value calculation. And my professor, we did so many iterations, and with the various research articles from Argonne Laboratory, we're able to understand that the recommended sample thickness is 0.8 millimeter, which we used for the experiment while applying some proper calibration through data analysis to minimize errors. Thank you.
Thank you very much. I can see the questionnaire nodding his head, so I think you have done a good job in answering that question. And the final question, the last by no means the least, coming from one of our own in here as well. How can your approach to pore connectivity analysis be adapted for fields where only drill cuttings are available and core samples are limited or absent? Considering the fact that the bulk of your presentation spoke to the use of cores, someone is interested to note if this is also going to be applicable to fields where only drill cuttings are available and the accessibility to core samples are either absent or limited at best.
That's an interesting question, and the way to answer this question is that if you, I don't know, I'm no longer showing my slides, but when for the USACs, which is ultras angles X-ray scattering, we use cuttings, and from that we're able to understand the pore size distribution. From 50 nanometer to micropores of less than 2 nanometer. So yes, with drill cuttings, even when you don't have cores, you can understand your pore types. And in terms of connectivity, if you look at your cumulative porosity, it can give you a qualitative indication of connectivity using your drill cuttings. And one other experiment I did, which I didn't show here, was gas diffusion experiment. So in the lab, we're able to use two methodologies, of which one of them is CO2 gas diffusion. I also did oxygen diffusion by exposing the data to the air. And from that experiment, you can analyze the results if you run it over 24 to 48 hours to determine your diffusion coefficient, which is an indication of pore connectivity. You can also determine the tortuosity using equations and permeability factor as well, including an air porosity and cementation factor. Yeah, you can do that because it has been demonstrated that is doable, which is part of this research project. Thank you so much.
Thank you very much, Dr. Azike. I want the House to please give Dr. a very resounding round of applause. It takes a researcher who actually did the research to be able to answer those questions in the way that he has done. And we want to really appreciate you for being a part of our technical meeting in this session. Thank you very much, and do have a nice remaining part of your day. I want to believe that we have eaten into your rest time, considering the part of the continent that you are in. So I want to thank you again for moderating your sleep to be with us. Thank you very much.
Thank you so much for the invitation, and I will be glad for next presentation you've given to me next month. Thank you so much.
Thank you very much.
Yeah.
All right. Okay, so ladies and gentlemen, those in the house and those online, we have come to the next part of this technical meeting where we'll be taking announcements from the Publicity Secretary, Mr. Stephen Sako.
Thank you, my boss, Mr. Dichi Ogbemi, for anchoring the meeting. And our participants, I want to believe we had a very good time listening to very incisive presentation by Dr. Azike. So for the announcement, and it's about the conference, since the president-elect is on the platform, so I want to crave her indulgence. It's my humble submission to call her to speak a bit about the conference before I will go about with the other part of the announcement. The president-elect, ma.
Hello? Hello?
Yes, we can hear you. Go ahead, ma.
All right, so thank you very much. Thank you very much for the presentation. I was in another meeting, so is it for my remark?
No, we want you to speak about the conference.
Oh, the conference. Okay. All right. Thank you very much, Benin chapter, for this session, and also the chairman and the presenter. Thank you. I've listened attentively, and I enjoyed all I've had today. It's quite insightful. So for 2025 conference, I'm sure all of you have been seeing our adverts. We have about 19 events lined up, which will kickstart tomorrow with the golf tournament at Uyo. And next week, Wednesday, will be the pre-conference workshop. And come Saturday, Friday, we'll have the virtual field trip. And Saturday, Sunday is the short courses. So if you are yet to register, we call on you to register now. And on the 10th, we will have on that same Saturday, 8th, we'll have the President's Night, and the icebreaker is on Sunday, the 9th. Then come 10th to 13th will be the conference proper, when opening ceremony will start on Monday, and thereby will end with awards night on Thursday. So if you go to our website, on our social media site, you see all the lined up programs, and I believe it's one that you won't want to miss. Please, if you are yet to register, quickly register now to secure your seat for the conference. Thank you very much. Do you have more flyers so that you can just span through everything so that everyone can see?
Yeah, we have more flyers.
Okay.
Yeah, don't mind the P.
Okay. Okay. So that's the end. So please go ahead and register. Thank you very much, and God bless you all.
Thank you, DP. Thank you very much.
Okay, thank you, PE. And I think you have said it all concerning the conference. So for the last thing that I needed to say before I step aside too is we call for membership dues. For you to be an active member of NAPE, you have to pay your obligation to the association. So we have all the different categories here for students and for active membership and associate and corporate membership. So you pay and notify us with your transaction receipt, and your records will be updated from our secretariat. Thank you.
So at this point, we'll move to the vote of thanks by the president. So Mr. Uche John Bosco, please, it's the time to give us your remarks. Vote of thanks.
All right. No, confirm you can hear me?
Clearly.
Okay, no, thank you very much. And good afternoon, everybody. I think I dialed in. So this one in particular, I know sometimes when I join the chapter technical meetings, sometimes there's in and out. But this particular one, I stayed in from beginning to the end, even though I was also multitasking in between. But at least I heard largely what the presenter actually gave every single one of us. And I really want to say a very big thank you for this opportunity, because when we talk about NAPE in terms of the knowledge base of the industry and having what it takes around the subsurface and the technical excellence, this is just one of it. Not just about research, but also coming out with results that will have impact to what we do as geoscientists. So I really want to say first thanks to the presenter and the speaker for today, but also thanks to the Benin chapter for providing this platform for our members and our friends and associates to be able to benefit from the lecture that we got today. And I like that element of the point that we've gone beyond, way beyond our ideas find oil. Our ideas find anything around energy, be it oil, be it gas, be it renewable. That's what we do. And wherever that knowledge is going to come, it should come. And that's exactly what has happened today. I also want to use the opportunity to thank everyone who has stayed on and the progress we've made. Actually, if I'm correct, but correct me if I'm wrong, President-elect, but this should be the last technical and business meeting we're having for the year. Yeah, I know we had for the one for Lagos about a week ago. Yeah. So that's correct. So this is so after this, all minds, definitely is going to be switching to the conference, which the PE already mentioned. Tomorrow the golf tournament starts, and then it begins to run until the awards night. When we take the ultimate, gala nights and awards night on that day. So I just want to say thanks. And again, it's a good privilege for Benin chapter for having that chance to be the chapter that is giving us the last technical meeting for the year. And I can only say, next year we will continue on the strong note that we're ending this year. So we've ended the technical meeting strong. I want to believe, and I'm looking forward to it, that next year we will kick off on these notes. Then I will be joining as IPP at the time. So thanks again, the Continuous Education Committee, led by the President-elect and the chapter coordinators have been involved getting this going, and every single one of you that has been part of our sessions from the beginning of the year till now. There is no other association you can think of that will give you the kind of benefits and value we continue to give. And we'll continue to do so and even continue to improve as time goes by. So thanks everybody that joined, and again, thanks the Benin chapter coordinator and the entire executive for getting this to this end. Back to you in the room, and back to you, Benin chapter.
Thank you. Thank you very much. Let's have this session where after now, the next activity is lab presentation, and after now we activity. So maybe after cut you off, so continue with other activities. Thank you.
Lab presentation, which will be presented events. The technical meeting ends with that plate presentation. So let's do that very quickly.
Thank you very much. We're here at this hall. What we're going to do now, we're going to present the plaque to the chairman of the